This content is produced by PASS the CSLB, an independent audio-first study companion for busy California B general candidates. I build these lessons from official CSLB study guide topics and reputable source-backed California materials so you can study on the go. This is exam prep reinforcement, not legal, professional, engineering, or job-specific advice. Exam content is set by PSI and the CSLB and may change, so always verify current requirements against official CSLB materials. No exam outcome is guaranteed. Now let's get into it. An electric vehicle capable parking space can be completely correct, even though it cannot charge a vehicle yet. That is the central distinction I want you to hold on to. In this condition, the project has reserved electrical capacity and a physical pathway for future work, but it does not yet have the complete branch circuit, the receptacle, or the charging equipment. The practical value is not what the space can do today. The value is what the building will not have to tear apart later. I think of this as the empty pipe principle. When walls are open, trenches are exposed, and concrete has not been placed, an empty raceway is inexpensive to coordinate. After the parking area is finished, the same missing pathway may require saw cutting, trenching, patching, and another round of trade coordination. I do not need to calculate conductor size or voltage drop to supervise this correctly. I need to make sure the approved pathway, panel capacity, termination, labeling, and sequence are present before the work disappears. The three readiness terms sound similar, but they describe three different scopes. Confusing them can create a bad estimate, a missing inspection item, or a handoff that does not match the contract. I put the three levels side by side because the cleanest way to remember them is by asking what physically exists. Electric vehicle capable is the foundation. It includes space in the electrical panel, enough planned load capacity to support a future branch circuit, and a dedicated raceway leading toward the vehicle space. The branch circuit conductors are not installed, and there is no required charging receptacle or charging unit at that stage. Capable means the route and capacity have been preserved. Electric vehicle ready goes one major step farther. The branch circuit wiring has been installed through the raceway and terminates at a receptacle or at the intended charger connection, depending on the approved design. Ready means the owner is not starting from an empty pipe. The electrical pathway has been turned into a usable circuit endpoint. Electric vehicle supply equipment means the actual charging hardware is installed. That is the wall unit, pedestal, connector, and associated equipment that transfers power to the vehicle. At that point, the project is no longer only preserving future capability. It is delivering charging equipment as part of the completed work. My memory connection is simple. Capable is the pathway. Ready is the powered endpoint. Installed supply equipment is the machine. Those words are not interchangeable, and the estimate should reflect the exact tier shown in the approved documents. For an electric vehicle capable space, the raceway cannot be treated like an ordinary convenience outlet run. The statewide baseline in the source material requires a minimum raceway of trade size 1, meaning a nominal 1-inch inside diameter. That minimum applies to the empty pathway that is being reserved for future charging infrastructure. The important supervision point is not to look at a piece of conduit and say that it seems large enough. I verify the specified trade size against the approved documents and the material actually delivered. A smaller raceway may look harmless before concrete, but it can defeat the future use that the project was supposed to preserve. There is a specific exception described in the source material. If a complete 40 ampere, 208 or 240 volt electric vehicle circuit is installed during original construction, the empty trade size 1 raceway is not required for that space, because the circuit is already present. I treat that as an either-or condition. Either the project provides the required future pathway, or it provides the completed circuit allowed by the exception. It should not provide neither and call the space capable. The raceway also needs a useful beginning and a useful end. It originates at the designated service panel or sub-panel area, and terminates near the proposed vehicle space in a suitable listed cabinet, box, or enclosure. A random stub with no coordinated termination is not the same thing as a complete future pathway. Then come the labels. The reserved overcurrent protective device space in the panel directory must be identified with the exact marking EV capable. The physical raceway termination at the parking location must also be permanently and visibly marked EV capable. One label identifies where future power will begin. The other identifies where the pathway ends. I want both ends to tell the same story, because a future electrical contractor should not have to guess which panel space and which buried route belong together. The highest risk of missing this work usually appears during sequencing, not during final electrical trim. Once concrete covers the route, the opportunity for a clean installation is gone. I use this sequence table as a pre-concrete coordination check. First, I confirm the approved scope and the planned panel capacity. Next, the excavation notification and utility responses are handled before digging. Then the earthwork trade opens the route, the electrical trade installs the raceway, and the work is checked before backfill or concrete. Only after the concealed pathway is in the correct place should the concrete trade close the area. Consider a hypothetical multifamily project with future charging spaces across a parking area. Suppose the concrete crew is ready, the forms are set, and the schedule is tight. The electrical subcontractor has not installed the raceway because the parking layout changed and nobody issued a coordinated update. Pouring anyway does not make the electrical scope disappear. It converts a coordination problem into demolition and rework. The field decision is straightforward. Before approving backfill, paving, a slab, a curb, or a charger base that will conceal the route, I verify that the raceway follows the approved path, has the required trade size, reaches the intended termination, and is ready for the required inspection. I also confirm that changes affecting the parking layout, panel location, charger location, or accessible route have reached every affected trade. Concrete is a permanent handoff. The trade that comes after it should not be discovering what the trade before it forgot. This is where the general building contractor earns the coordination role. The earthwork subcontractor controls the trench, the electrical subcontractor controls the raceway, and the concrete subcontractor controls the final cover. My job is to make sure those scopes meet in the correct order. I do not let the schedule turn sequence into guesswork. Underground electric vehicle infrastructure is still excavation work, even when the final product is only an empty conduit. The soil hazard does not change because the raceway has no conductors in it yet. Before excavation, the excavator must contact the Regional Notification Center, commonly reached by dialing 811 at least 2 working days before digging. The source material also calls for positive responses, so existing underground installations can be identified before the excavation begins. That protects the crew from treating an unknown utility path as open ground. Depth creates another clear supervision trigger. When employees enter an excavation that is 5 feet or greater in depth, they must be protected from cave-ins by an adequate protective system unless the excavation is entirely in stable rock. The permitted approaches described in the source material include shoring, shielding, such as a trench box, and proper sloping or benching. I want to be precise about what that number means. 5 feet is the protective system trigger taught in this lesson. It is not permission to ignore conditions in a shallower excavation. Soil condition, adjacent loads, water, vibration, and signs of instability still matter. A competent person must inspect the excavation, the adjacent area, and the protective system before the shift and as conditions require. The trigger gives a minimum rule. Field conditions still demand judgment. Imagine a crew saying that nobody will be in the trench for long, so protection can wait. Duration is not the control. Exposure is the control. If an employee enters a qualifying excavation, the protective system must already be there. I keep the order simple. Locate utilities, evaluate the excavation, install protection when required, and only then send people into the work area. When the project moves from capable to ready, or to installed charging equipment, the electrical safety checkpoints become visible at the finished location. The general building contractor is not expected to design the circuit, but should recognize whether basic protective features shown by the code and approved design are missing. For electric vehicle charging, single-phase receptacles rated 150 volts to ground or less and 50 amperes or less require ground fault circuit interrupter protection for personnel. A heavy-duty receptacle is not automatically outside that rule just because it serves an electric vehicle. I verify that the electrical specialty contractor has addressed the protection required for the actual receptacle and circuit configuration. A receptacle installed in a wet location also needs a weatherproof enclosure that maintains its weatherproof integrity, whether the attachment plug is inserted or removed. A cover that protects the receptacle only while nothing is plugged in does not satisfy that condition. The practical inspection question is whether rain protection remains effective during normal charging use. I connect these two requirements by thinking about the user standing next to energized equipment outdoors. Groundfall protection addresses a dangerous leakage path. The in-use, weatherproof enclosure keeps the receptacle protected while the cord is connected. I do not have to become the electrical designer to notice an exposed outdoor receptacle, a missing protective cover, or a scope that never included the required ground fault protection. Panel capacity is part of the electric vehicle readiness before any charger appears on the wall. An electric vehicle capable space requires planned load capacity and reserved panel space for the future branch circuit. An empty conduit without capacity at the source is only half of the promised infrastructure. Large multifamily and commercial projects create a different challenge because many vehicles may need charging, while the building has limited available service capacity. The source material permits an automated load management system to reduce the overall electrical load capacity required at the service panel when multiple vehicles are charging. The system monitors available power and allocates charging load across the connected equipment, rather than assuming every charger will draw its maximum at the same moment. I do not treat an automated load management system as a field shortcut or a substitute for approved electrical design. I treat it as a coordinated project strategy that must appear in the electrical scope, equipment selection, controls, and commissioning plan. The electrical designer and electrical specialty contractor handle the technical design. The general building contractor makes sure the strategy is actually included in procurement, installation, networking when required, and final turnover. The common estimating mistake is assuming that every additional charger automatically requires a separate full capacity increase at the building service. Sometimes a utility or service upgrade will still be necessary. The source-backed distinction is that an automated load management system is a permitted way to share available capacity, so it must be evaluated before the project assumes that a major physical upgrade is the only path. At public buildings, commercial facilities, and public housing, charging infrastructure is also an accessibility coordination problem. I want you to see it as a route, not merely as a striped parking stall. The accessible electric vehicle charging space must connect to the charger and to the facility entrance through a continuous, unobstructed, accessible route. That means the charger cannot be placed where a curb, wheel stop, pedestal, bollard, slope, or parked vehicle blocks the required path. The concrete, paving, striping, and equipment locations all have to work together. The source material also permits certain vehicle spaces to share a common access aisle when the code conditions are met. That can be an efficient layout, but it does not remove the need for the aisle to adjoin an accessible route and receive the required markings. I do not assume that a standard accessible parking layout automatically satisfies the charging layout. I verify the approved Chapter 11B details for the actual project. This is another reason the conduit route cannot be coordinated in isolation. Moving the charger pedestal to avoid an underground conflict may change the accessible route. Moving the access aisle may change the concrete and striping. Moving the parking space may change the raceway length and termination point. One change can cross electrical, concrete, paving, and accessibility scopes at the same time. The legal scope boundary matters before any estimate goes out. California Business and Professions Code, Section 7057, does not turn a general building license into permission to take every single trade project as the prime contractor. I use the scope matrix to separate a standalone electrical job from a qualifying multi-trade project. A contract only to mount, wire, and energize one electric vehicle charger is electrical work. A general building contractor cannot take that electrical-only prime contract unless the contractor also holds the required electrical specialty classification. A larger project can change the answer. If the scope genuinely requires at least two unrelated building trades, the general building contractor may take the prime contract and coordinate the overall work. A project involving earthwork, concrete, and electrical installation is a clear multi-trade example. The general building contractor can superintend the sequence, while properly licensed specialty contractors perform the specialty scopes. The source material also warns that framing or carpentry does not count toward the two unrelated trades used to qualify the prime contract. I do not add a token carpentry item to an electrical job and pretend the licensing boundary disappeared. The scope has to be real, and the unrelated trades have to be part of the actual project. Consider a homeowner who asks only for a charger on an existing garage wall. That is the single trade situation. Now consider a separate project that includes a new concrete parking extension, underground earthwork, and the electrical charging installation. That is a coordinated multi-trade project. The physical charger may look similar in both cases, but the legal contracting scope is not the same. I close this topic with one field question that works at every handoff. What must exist before the next trade covers it, depends on it, or prices around it? Before excavation, the utility notification and responses must exist. Before a worker enters a qualifying trench, the required protective system must exist. Before backfill in concrete, the raceway route, trade size, and termination must exist. Before final sign-off, the permanent panel and termination labels must exist. Before an owner expects immediate charging, the project must be ready or have charging equipment installed, not merely capable. Before the general building contractor signs the prime contract, the license scope must fit the real combination of trades. The central memory line is still the same, conduit before concrete. Then add 3 short distinctions. Capable preserves the pathway and capacity. Ready adds the completed circuit endpoint. Electric vehicle supply equipment adds the charging machine. If I keep those distinctions clear, the estimating, sequencing, inspection, and scope decisions become much easier to organize. This is a testable concept based on the published Contractor State License Board study outline because it sits at the intersection of electrical coordination, planning, concrete sequencing, earthwork safety, accessibility, and legal scope. I do not need to wander into conductor calculations to apply it as a general building contractor. I need to recognize the required condition, coordinate the licensed trades, protect the work before it is concealed, and verify the final handoff. I made an audio practice quiz specifically for this episode so you can check whether these distinctions are sticking. It is audio-based, the questions are read aloud, and you answer by tapping, because I know a lot of your studying happens while you're driving, working, or otherwise on the go. Go to the description below this video. You will see a link that says Pass the CSLB. Tap it. It will take you straight there. Comment below with any questions about the material I covered, and subscribe so I can help you stay on track through every episode until you get your license. I am rooting for you, and I want you to finish this process with the confidence that comes from understanding what each field decision actually controls.